All right, in this video, we're going to be going over two topics. The first topic being the black box approach and how you can use it to create the entity inside of VHDL, henceforth making the architecture creation easier. And then afterwards, I'm going to be showing the synthesis coding guidelines to a combinational digital circuit. Okay, starting with the black box approach. The black box approach isn't just used in the world of digital design. If you've taken operating systems, I think one of the exercises is used for unit testing, and they bring up the whole black box idea there. The idea of the black box approach is not caring about what's under the hood. So how we're applying it here, if I want to go into VHDL and I know I want to make an adder circuit. Now this example may seem redundant at the fact that an adder circuit is going to be super easy to implement, but we're going to use the sake of simplicity for the sake of just showing the black box approach, which is the focus of this. So if I go and say I want to make an adder circuit, by creating the black box approach, I'm going to have one input, a second input, and then an output. That's literally all the black box approach is. You want to have a black box, you draw your inputs and your outputs. For an adder, I just want to add two numbers together and then get an output. It's going to be a bus of 16 bits for both. With this is all I need to be able to make that entity that I was referring to in the previous video, where I say there's two main components of a VHDL file, an entity and an architecture. The black box approach is what allows you to figure out what you need in the port for your entity. So like I have in the graphic, X and Y as inputs, both 16 bits, and then out as an output, also 16 bits. Coming back here, it's exactly what I have. X and Y, both as inputs for standard logic vector, 15 down to 0, including 0, that's 16 bits. And then Z. Now that we have the entity, we can move on to the architecture portion. I'm not going to go into the details of exactly how I created this, but know that there is some casting type concepts that are going to be you're going to need to know for VHDL because VHDL is a strong coding language, meaning you have to be very explicit with what you're doing, and VHDL doesn't handle any of these casting. I'll put a link to an article on a website called Nanland that will go into a bunch of different examples of casting that you probably will ever encounter. Before moving on to the synthesis coding guidelines for combinational digital circuits, the last thing I want to say about this adder is that this is a behavioral architecture, simply because I'm describing the behavior of this adder circuit. Now, to explain the synthesis coding guidelines for combinational digital circuits, I'm going to be doing a 2x1 mux, because it will allow me to show both guidelines that are needed for combinational logic circuits. Now, to kind of reiterate what we're going over before, we have two major portions of VHDL. The entity, which for mux, you have two inputs and then a select line. It's a third input and then an output. And then the second main portion of the VHDL is an architecture. Again, this is a behavioral architecture simply because we are describing the behavior of the circuit. Now, the important part is the synthesis coding guidelines. Now, what the synthesis coding guidelines are is that they are guidelines created by Dr. Stitt, where he found the best ways of creating a synthesizable circuit. Now, what that means is when you go into Quartus and you compile, multiple things are going to occur, such as compiling really just checks for analysis just checks for any syntax errors to see if your code can actually be synthesized. Once those errors are confirmed to not exist, it's going to synthesize the circuit, mean put it onto or figure out how to put it onto the board with routing. Now, a set of VHDL code cannot have or can have no syntax errors, but then go onto the circuit and have random behaviors where the circuit doesn't work. And that is where the synthesis coding guidelines come in. How to make a synthesizable circuit, meaning a circuit that can be put onto a physical board and work correctly. So a lot of students have been encountering one of these guidelines by not following them in lab 3 with the FSM. And that is the second synthesis coding guideline, which is all outputs must be defined on all paths through a process. Now, kind of starting over from the top, these are the synthesis guidelines for combinational logic specifically. Later on in one of the next videos, I'm going to get into sequential circuits. You treat sequential circuits differently from combinational circuits. Remember how before I was describing there are two architectures, behavioral and structural. So far, I've only gone over behavioral architectures. Specifically, I have only yet to cover combinational circuits in a behavioral architecture. So when you're creating a combinational circuit, you want to follow these two synthesis coding guidelines. The first one being all inputs to the combinational logic must be included in the sensitivity list. So we look at the ports, we got N0, N1, and select are the inputs. So we see here the sensitivity list, all inputs are in the sensitivity list. And that makes sense because we want the process to execute each time one of these inputs changes. The second synthesis coding guideline is that all outputs must be defined on all paths through a process. If there exists a path that defines an output, sorry, this is incorrect, that doesn't define an output, that output will become a latch during synthesis. So the reason I decided to show the mux is that, for example, in the FSM, most students are doing the win case statements, and what they're doing is that they're never having, or there's a certain path where one of their outputs isn't defined. So if I were to have, for example, just this in my if branch, accounting for select 0 and select 1, and I didn't have this else here, there'd be possible branches in which an output doesn't exist for the output value. But since I'm adding this else here, I'm covering all possible output branches. So basically, a catch-all net is that if you have this sort of case type if branches sort of thing in your VHDL, you can just have an else or others type case to account for any of the other possible outputs or other possible paths. And then along with that, the second approach is having default values. For example, I could have a default value for output here of whatever I want it to be N0, knowing that if it actually is select 1, it'll just be overwritten by N1, which is another idea of outputs in a process. The output of the process is going to change at the end of the process. So for example, here, if I come into the process and select is 1, output is going to be assigned N0, but it doesn't matter because we come into this if branch, select will be 1, output will get assigned N1. So the only thing that matters at the end of the process, output is going to exit with the value of N1. So that's it for this video. We covered the black box approach, which you want to apply to any circuit you're going to create. It allows you to easily figure out what you need in the port section of your entity. And then we went on to cover synthesis coding guidelines for combinational logic.